Ask a language model for a controversial strategy or a restricted line of code, and it will output a predefined apology. It refuses. But if you know exactly where to look, you can shatter that refusal mechanism and run the exact same prompt. The model will immediately output a detailed answer with zero retraining. Alignment techniques like reinforcement learning from human feedback and direct preference optimization are treated by the industry as deep behavioral constraints. The assumption is that these methods modify the model's core intelligence to enforce safety. Following that logic, removing those constraints should require massive compute clusters to run thousands of hours of complete model fine-tuning to rewrite the weights from scratch. The data shows otherwise. Refusal behaviors do not spread through every part of the network. They anchor themselves in highly localized, low-dimensional subspaces within the model's mathematical geometry. We can extract the specific directional vector that controls those subspaces and mathematically zero it out, leaving the rest of the network untouched. This technique is called obliteration. When refusal is treated as a geometric artifact instead of a behavioral rule, control of an open weight model transfers directly from the corporate lab that trained it to the engineer deploying it on local hardware. To execute this process, researchers rely on OBLITERATUS, an open-source toolkit built to automate the extraction and targeted projection of these refusal subspaces. Early ablation tools relied on blunt, single-pass weight modifications. They often removed the refusal but triggered catastrophic forgetting, causing the model to lose logic and language capabilities simultaneously. OBLITERATUS applies the principles of mechanistic interpretability. Rather than acting as a simple jailbreak script, it operates by dissecting and mapping the internal logic of the transformer architecture. This schematic outlines the system's four-stage operational pipeline: probe, distill, excise, and verify. These stages function together as an analysis-informed closed feedback loop. The pipeline scans the target model and actively auto-configures its parameters to match the unique layer structure it detects. Precision here is necessary. Cutting blindly inside a large language model's dense weight matrices will irreparably sever its reasoning engine. The pipeline begins with the probe stage. The objective is to map the physical anchor point of the refusal mechanism. It runs parallel forward passes through the model using paired sets of prompts, one strictly harmful, one harmless. Tracking both streams simultaneously, the system collects and maps internal tensor activations, searching for the exact moment the model's behavior diverges. To analyze this divergence, the system deploys a diagnostic module called the Refusal Logit Lens. This lens isolates the specific layers actively calculating the decision to refuse, separating them from the adjacent layers that are merely processing syntax and language structure. The resulting map reveals the geometry of the guardrail, specifically whether the model relies on a single refusal mechanism or if it splits its safety checks into multiple distinct categories. Establishing this map ensures the upcoming mathematical surgery removes the intended target without deleting the factual knowledge stored nearby. Once the coordinates are mapped, the pipeline shifts to the distill stage, converting millions of raw data points into a single mathematical vector. This chart shows the baseline method for identifying that vector, calculating the difference by subtracting the means of the harmful and harmless activations. But natural variance and operational noise continuously shift the calculation, causing the vector to blur out of alignment. To solve this, OBLITERATUS implements a filtering technique called whitened singular value decomposition. By applying covariance normalization before executing the singular value decomposition, the system filters out standard model variance. This isolates a stable, sharp vector. Training algorithms like DPO or constitutional AI leave distinct geometric imprints on how a refusal subspace is compressed. By measuring the orientation of this pure vector, OBLITERATUS can fingerprint the specific alignment method used to lock the model. Using a noisy vector to edit a model's weights causes collateral damage. A covariance normalized vector is required to execute a precise cut. With the refusal direction isolated, the pipeline initiates the excise stage to modify the targeted weight matrices. This visual represents the mathematical action, applying an orthogonal projection to zero out the isolated refusal direction within the model's targeted layers. Because multi-layer perceptron blocks are highly sensitive to modification compared to attention layers, the system applies component-specific scaling to regulate the projection strength. However, zeroing out data creates a computational hole in the matrix. If left untreated, this hole lowers the model's overall coherence and perplexity scores. To prevent this capability collapse, the toolkit deploys a safeguard known as norm-preserving biprojection. The system calculates the exact mathematical norm of the matrix prior to projection, and once the data is excised, it restores that norm across the remaining weights. Restoring the original mathematical volume ensures the refusal is removed, while the model's baseline reasoning capabilities remain intact. Modern alignment techniques are robust. To ensure the intervention holds, the pipeline moves to the final stage, verify. Standard single-pass projection methods often pass initial tests, only to fail when pushed with edge case prompts. This is the Ouroboros effect, a model's tendency to self-repair its guardrails when an internal layer is altered. When one layer goes dark, adjacent layers actively rotate residual refusal signals into new mathematical subspaces to compensate for the missing data. The verify loop monitors the stack, detecting this rotation by measuring exact spikes in KL divergence. Detecting the Ouroboros effect automatically triggers targeted iterative refinement passes, chasing the residual signal through the network until the rotation is neutralized. Securing total refusal removal requires treating the model as an adversarial, self-correcting system. Running this degree of mathematical analysis demands hardware overhead, creating VRAM requirements when targeting models exceeding 400 billion parameters. Because the pipeline relies on thousands of sequential forward passes to map the activations, traditional data parallelism strategies failed to split the compute load. Instead, the system uses naive pipeline parallelism, sharding the model sequentially across multiple GPUs to hold the volume of weights in memory. This hardware execution powers the project's ultimate ambition. It is designed to operate as a distributed, crowdsourced research experiment. Every time a user runs the pipeline with telemetry enabled, they contribute anonymous geometric configurations and performance data back to a central hub. That aggregated data builds the universality index. The index provides the scale required to determine if refusal mechanisms generalize across architectures, or if each individual model demands bespoke mathematical intervention. This open-source pipeline converts model behavior from a locked behavioral trait into a malleable geometric property, governed by the engineers who deploy them.